1000 times 5, because it's not pipeline. Average, okay, in the non pipeline, so you can say, okay, now please remember, I will explain this. You know, for the students who are not there, please look at here. Please look at here and try to solve it. I will ask one question relevant to that. Okay, so now we have how many instructions are there? 1000, so it means that we have I1. I1 is instruction fetch, decode, execute, main memory, write back. I1 will be executed in how clock cycle? How many clock cycle? Tell me. 5. Then I2, fetch, decode, execute, main memory, write back. I'm just like talking to you like children, like for children. How many clock cycle? 2. So let's assume if we have I1000. So the total clock cycle in a non-pipeline machine will be what? How many instructions are there? 1000. And how many clock cycle will each instruction require? 5. There is no overlapping in the non-pipeline. So what will be the clock cycle in non-clock cycle? How many clock cycle will it take? Tell me. 5000. Please remember, in non-pipeline machine there will be no hazards. There will be no hazards. Please, because they are doing it one by one, so they will. It is not overlapping. Because then in this case, this I1 and I4 will be not overlapped. But in pipelining, we are overlapping them. That's the reason that in non-pipeline, there will be no structural hazard. Okay, now, how many load instructions are there? What is the percentage of the load instruction? 20%. So total load instructions. So total load instructions. Load or store instruction. It is actually 20%. So it is actually 20 divided by 100 multiplied by what? 1000. So how many load instructions are there? Load or store? 200. So 200 instructions are load and store. And please remember, for one load, here, how many loads do we have? 1. How many stalls do we have? 1. If we have more loads, it means we will have more stalls. So the total number of stalls due to load. So total load and store instruction are 200. So total number of stalls. How many stalls are there due to load and store instruction? 200. So we have 200 stalls. Extra clock cycles. Remember? And please remember, if we say how many number of clock cycle in the pipeline machine? So the clock cycle in pipeline is 60. So please remember the formula. If you remember the formula, your life will be easy. So if we have the clock cycle in a pipeline machine, if you have the number of clock cycle in a pipeline machine, okay, so what is the formula? Help me.
The instructions plus stages.
K plus D plus S minus 1. What is K? We discussed it in the last lecture. What is K? Number of instructions. What is D? The number of stages. What is S? The number of stalls. So K plus D plus S minus 1. So what is K? 1000. What is D? 5. S? 200. Minus 1. So what is now the thing? 1204. 5 minus 1. Got it or not got it? Okay, I will explain this. Okay, now please remember why I'm going to do. So please remember why I'm repeating it using multiple methods, multiple things. So basically, should I rub this off? Okay, so now I will explain this. Okay, so how I will now prove it through the visual representation. Now I'm doing it with the visual representation. In the visual representation, we will have I1. This is my non-pipeline machine. If it's my non-pipeline machine, how many clock cycle will I1 take? Help me. How many clock cycle? 5. I2? How many clock cycles? So if it's I1, so I1 is actually fetch, decode, execute, main memory, write back. Is there any overlap? No overlap. Then we have I2. Fetch, decode, execute, main memory, write back. No overlap. Then I3. Fetch, decode, execute, main memory, and write back. No, so it means if we have 1000 instructions. So the total number of clock cycles is what? The total number of clock cycles is 1000 multiplied by what? 5, which is actually 5000. So this is actually this thing is the clock cycle in non-binary machine. Clear or not clear? Clear? Okay. Now for the second example. Now we have a pipeline machine. So we have a pipeline machine. Okay. Please remember, now we have a red color. Red color is for the load or store instruction. So this is a load or store instruction. So this is I1. If it's red color, so it means we have fetch, decode, execute, main memory, and write back. And the blue color is for any other instruction. So I2, fetch, decode, execute, main memory, and write back. Then we have I3. I3 is also a load instruction. We have fetch, decode, execute, main memory, and write back. Now we have I4. I4 is a non-thing. So we have fetch. This is fetch, decode. Okay. So can we fetch I4 with I1? Can we overlap I1 and I4? What is the red color means? What does red color means? Help me. Red is load or what? Store. And the green one, so the blue one, which instruction? Any other instruction. It can be add, subtract, any other instruction. Any other instruction except load or store. Can we overlap this I1 with this memory? So can we overlap them? Yes or no?
Yes.
If we have a combined memory,
Okay. Oh, yeah.
we cannot overlap them if we have a combined memory. If we have a combined memory, so what we need to do? We need to put what? A stall. And for stall, I put S. So this is actually S, 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 S. Now we have I4. Now if we have I4, which is not, so we can fetch I4 from here. Fetch, decode, execute, memory, and write back. Now we have I5. I5. If it is actually fetch, decode, execute, memory, write back. Can we overlap this with the red instruction? Can we overlap them? Look at here. This is my load instruction, load or store instruction. Can we overlap it with the fetch instruction? Yes or no? No. What we need to do? Stall. So if you put a stall, so basically we need a stall cycle. If we need a stall cycle, so it will be S, stall, 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 stall. And the stall has to proceed through all the stages of the pipeline. Then, can you see here, if we have, okay, now we have I5. Please remember, we cannot overlap this red instruction with the blue instruction. So it means we cannot, if it is in the man memory state, this will be in the fetch stage. So we cannot overlap them. So now we can have an ILAP. So can you see here? So we have fetch, then we have decode, then we have execute, then we have memory, and then how many stalls are there? Here, how many stalls are there in this example? 2 stalls. Why 2 stalls? Because to load or store instruction. So if we have more load or store instruction, so if we have more, so it means we have an extra clock cycle here and an extra clock cycle here. Clear or not clear? Okay, this is for the combined architecture or for separate architecture? Combined. But if you have separate architectures, okay. Now how many clock cycles are there here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So now if we calculate this, how many clock cycles are here? Help me. 11 cycles. Now we have 11 clock cycles. But what if we have a separate instruction and memory? So now I'm now reproducing it. I'm reproducing it. Now we have I1. If we have an I1, I know that some of the students are busy in their stuff, and basically it will ruin your quiz 3. It will ruin your quiz 3. I'm telling you. I'm telling you. So we have fetch, decode, execute, main memory, and write back. This is my first instruction. Then I2. Okay, this assumption is for combined memory or separate memory? Combined. And now we have separate. So if we have separate memory, do we have stall here? No, we will not have a stall here. So even if we I2 will have fetch, decode, execute, main memory, and write back. Then we have I3. Fetch, decode, execute, main memory, and write back, because there will be no stop. This main memory, this okay, and then I4, the blue color. Fetch, decode, execute, main memory, and write back. They can overlap now. They can overlap. And then we have what? Which instruction? I5, fetch, decode, execute, main memory, and write back. How many clock cycles? 1, 2, 3, 4, 5, 6, 7, 8, 9. How many clock cycles are there? Here, how many clock cycles are there? 11. So how many stalls are there? So generally now I have proved with a small example. I proved with a small example that if we have n load and store instruction, if we have n load and store instruction, so it means then if for a combined main memory, how many stalls will we have? How many stall cycles? N stall cycles. But if we have again, this will be the question exam. If there are n load and store instructions, and if we have a separate instruction and data memory, how many stall cycles will be there? 0. Here, how many stalls are there? Stall cycles are 0. 2 here. And here, how many stall cycles? 0. So stall cycles are. Here, how many load and store instructions are there? 2. It means how many load and store instructions are here? 200. So how many stalls will be there? Clear or not clear? Now, what will be the speed up? Anyone may answer. What will be the speed up now? Help me. Please remember, the speed up compared to the non-pipeline machine will be equal to the clock cycle. This may be the question in exam. So the clock cycle of pipeline, non-pipeline divided by the clock cycle of pipeline architecture, and the non-pipeline, what is the clock cycle? 5,000, and then what? Divided by what? 1204. What will be the final answer? 4.15. Okay, what should be the ideal speed up? The ideal speed up should be close to what? 5. The ideal speed up should be close to 5. But the problem is, this may be also the question in exam. Okay, so now this is the ideal speed up is actually close to 5. But if there are small cycles, the speed up will be decreased. Clear or not clear? Any question?